Dear students, today we will be discussing the Unit 3 of this course, which is Fiber Optics and Laser Systems. So far, we have discussed about how a laser system works, how lasers are created, and all the physics surrounding the laser. Now, this is one important application of lasers, and that is holography. So we'll define holography, and then we'll discuss coherence in more detail uh, to show how important coherence is to get a good holographic picture. So to start with, uh, let me first show you the complete syllabus of this holographic unit. And in this video, we will be discussing only the introduction to holography and then about coherence and its importance. Rest of the subtopics will be discussed in the next video. So, a hologram is a recording in a 2 or 3 dimensional medium of the interference pattern formed when a source of light, that is reference beam of fixed wavelength, encounters light of the same fixed wavelength arriving from an object beam. So whatever I read here, if you read it again in the context of this diagram, then the concept of the hologram will be more clear to you. You might have seen a holograph, right, where you see a 3D picture. When you see from different angles on the picture, you see different images, different intensities. How does it happen? How is it different from a photograph? So if you see those differences, you will be able to appreciate what a holograph is. So let us first see about a photograph. A photograph is a record of distribution of optical density given by intensity only. That means what we see in a photograph is the distribution of the intensity of the image of the object on a plate in x and y direction. That's all. There is no information about the z-axis. That means it has no information about the depth. It is just a 2-dimensional projection of a 3-dimensional object. You can take an example from my image. See, if you want to take a photograph of mine, I am a 3-dimensional object, but whatever you get in a photograph is a 2-dimensional distribution of uh, my area, which is being exposed to the light coming from this object. So this is a 2-dimensional representation of a 3-dimensional object. Now, so it has only an information about the intensity of light from my different areas. Now, the holograph is a record of the phase information as well. Because if you see me as an object, then this is my front image, and if you see the depth, then the light coming from this and coming from this will have a path difference, and this path difference will convert into a phase difference. And if this phase difference can be recorded, then you are able to see this depth also, or this depth also, or this depth also, further depth also. So so the phase information is important. So a holograph is basically a record of phase information as well. That means in addition to the intensity representation, if phase is also represented on a plate or on a recording medium, then it becomes a holograph. And for this to happen, we have to have an interference pattern between two sources of light, one which is coming from the object and the other which is coming from a reference source. And the best example you can see here is that you have a photographic plate and the object is here like me. Now one light is coming from the object and falling on the plate. So this, as far as this falling is concerned, this is a photograph simply. But if I introduce a reference wave coming from another source, but of same wavelength, right, or with a fixed phase difference, then these two waves, the wave coming from the object and the wave coming from the reference source, will interfere with each other and form fringe edge, right? The maxima minima which you have might have studied during your BSc or your lower courses. So the interference between these two waves gives you the phase information also, right? So intensity will consist of, because of this interference, the intensity which will be available, the value of intensity which will be available will include the phase information also. So that is how we term the holograph as having informations on the intensity as well as on the phase. So for interference to happen, we need coherent light sources, both for the object and for the reference source, especially for the object. Now, a good appreciation of coherence will help better understanding of interference for creation of holographs. So, what did we get from this slide is that we need to understand more about coherence. So, these details and about the basic concepts about the hologram is also given in this reference, as you can see later on. So let's go to the second slide. Now we'll be talking about the coherence. Uh, Coherence has a general meaning also if two persons are speaking in same uh, phase. That means they have the same opinion or they have the same phase difference. That means about their frequency of speaking. Then these two people are considered to be coherent, or their voices are considered to be coherent. Or sometimes this terminology is used to depict the characteristics of a person who is incoherent. Let's say a person speaks something uh, at one moment and on the same topic he speaks something different at the other moment. Then this person is incoherent in his views. Now I hope you get the difference between the coherence and incoherence. Now, as far as the electromagnetic waves are concerned, two electromagnetic waves having slightly different frequencies or slightly different phases between them, but they are fixed frequency difference or fixed phase difference, are said to be coherent. And if they are coherent, then the interference between these two waves is possible, and a very good interference rings will be observed, which you might have seen in the Young's double slit experiment during your undergraduate studies. And you can see a very good example here. Let's say this is a one wave which has a particular node antinode position, right? And this is all along its passage propagation. Similarly, if we have a second wave, this wave is different from the first wave, yes, but its node and antinodes, its phases are different from the first wave, but they have a fixed difference. That means the second node is having the same difference from the first one. And similarly, if you have a third wave, this also has a different frequency, but this frequency is constant along its propagation. So these three waves have different frequencies, have different phases, but they are fixed. And if they are fixed, that means these we will call these three waves as coherent electromagnetic waves or coherent light sources. Now, when these waves propagate along a distance, they get disturbed in the atmosphere because of several reasons, scattering, or diffraction, or whatever, and then there is some change in the phase of one wave or the other. When this happens, then what happens is that they they lose the coherency, and at that point of time the coherency is reduced. So we define a factor tau c as a coherent time till which time the coherence is maintained, and there is never a perfect coherence. So we define it in terms of a degree of coherence, and this can be defined in terms of tau c also. So This coherence is defined in two types. One is the temporal coherence and other is spatial coherence. And I forgot to mention, this is written here also, when complete coherence is not achieved, but still some interference takes place, because this interference will not be that good as in case of an ideal coherence, but of course interference will take place. So that means this interference will also be partial interference, because there is a partial coherence, and this partial coherence will occur because of the maintenance of coherence in two terms. One is temporal coherence, other is spatial coherence. What is temporal coherence? Temporal coherence is associated with difference in phase of two waves, and it is also referred to as a longitudinal coherence. That means when two waves are moving in the same direction, and as I explained in this above, then these two waves are having same phase or a fixed phase difference. After certain amount of time, because of some losses in one of the waves or both the waves, their phase difference changes. And if this phase difference change is beyond a certain limit, where we can define the coherency to be stopped or coherency gone down, then that time limit is called the coherence at a coherence time or time of coherence, right? And since both waves are going in the same direction, so this we call as a longitudinal coherence. The other coherence is spatial coherence, which is along the y direction. That means along the transverse direction. That means when two waves are far apart, and when they are far apart, they will have a path difference and hence a phase difference. And again, after covering a certain distance, that means after covering a certain amount of time of propagation, they will lose their coherence. So that will be described in terms of spatial coherence. So let us discuss the temporal coherence. This type of coherence refers to the correlation between the field at a point and the field at the same point at a later time, right? So that means if you are observing a wave at a particular location, and then you are observing the field at a certain time which is different from that particular time but at the same location, then if there is a phase difference between the two which has changed, and if this phase change has gone much become much larger, then the coherency has stopped. So this time till which time the coherence is maintained, the phase difference is fixed phase difference is maintained or is maintained within a limit, then this is called coherent time, right? And this such type of coherence is called temporal coherence, and the time tau c is referred to as coherent time, and the length of the wave train, that means the distance covered by the wave train during that coherent time, is called the coherence length or coherent length or longitudinal coherence length, which is LC equal to C tau C. So that means what does it say? That if we know the coherent time of of a coherent source, or having coherent waves or having coherent sources, we know that coherent time. That means we know for how much long distance they will travel being in coherence, right? So till that time they will be able to cause interference between them, and that is what we want. So it can also be shown that a wave having a coherence time tau c is essentially a superposition of harmonic waves. So for example, if the resonant frequency is nu zero of a laser light source and its bandwidth is delta nu, right? So delta nu is inversely proportional, approximately equal to 1 upon tau c. This is the coherent time. So what does it indicate? It indicates that if you have a larger coherent time, That can happen only when you have a very small bandwidth. That means you are giving less chances to other frequencies because the bandwidth is very narrow. Sharp laser beam has a more chance to be coherent. So now we go to explain further on this temporal coherence. So for a well-controlled laser, if delta nu is 500 hertz, that is bandwidth. So our tau c can be calculated. You just divide by c. This becomes 2 into 10 to the power minus 3 seconds, and therefore coherence length is c tau c equal to 6 to the power 10, 6 into 10 to the power 7 centimeter, which is 600 kilometer. That means if a laser beam has a bandwidth of 500 hertz and its coherence time is 2 into 10 to the power 2 milliseconds, then it has a coherence length of 600 kilometer. That means such a laser beam can have interference pattern up to 600 kilometer. That's a very good point, very good observation. That means holographic image can be obtained to that particular distance, because interference can be created up to that distance. So this long coherence length implies that laser could be used for performing interference experiments with large path differences. Right now, here in this section, we are correlating the coherence length with the laser frequency as well as the bandwidth. So what does it indicate here? It's a very simple derivation. I'm not going into that detail. You can cover it. But what is important here is that for a longer wavelength, even if the bandwidth is higher, the coherence length will be higher. And if the bandwidth is lower, then much better, right? So for a longer wavelength means for red laser, infrared laser, the coherence length is much higher, right? For a shorter wavelength, it will be slightly lesser. So you can well differentiate between the different type of spectral characteristics of laser beams, right? Now, this was as far as the temporal coherence is concerned. Now we talk about the spatial coherence. Spatial coherence describes how far how far apart two sources, let us see here in this drawing, S1 and S2, two sources or two portions of the same source. Let's say S is the same source and its two portions are S1 and S2. So same source can be located in a direction transverse to the direction of observation and still exhibit coherent properties over a range of observation points. So such two sources are said to be spatially coherent, and you can further define it in terms of two fields at two different points on a wavefront. Yes, this can be considered as a wavefront also, right? So they are considered to be space coherent, spatially coherent, if they preserve a constant phase difference over a distance or over a time period, tau c, as we discussed in the temporal coherence. If they maintain a coherence, then they are considered to be spatially coherent, right? So this is possible even when two beams are individually time incoherent. Individual beams may be time incoherent. That means they are not coherent with respect to phase. But as long as any phase change in first one is accompanied by a similar phase change in the second one, that means phase change is fixed and its duration is fixed, then they can be spatially coherent because that phase change will be reflected uh, over a distance. Same phase change will be reflected over a distance over a particular coherent time. So this is only possible if the two waves have been produced in the same part of the source. Although whatever we discuss is in an ideal case, so practically if you take two waves from the same source, like these two sources from the same source, and these two are apart, a distant apart. So they will create an image not along the direction of propagation, but at a certain distance away from the axis of that propagation. So this there is, if such things happens, and if they are spatially coherent, so the interference pattern will still be observed, and you can very well see the example of Young's double slit experiment. So what, and this condition is derived here, that in order to have a spatially coherent source, you have to have a condition of D. D is the distance between these two sources, and you can consider these two sources as S1 and S2 as your two eyes. Then it will help you further. So these are S1 and S2, and the observation is at a distance capital T, and L is the width of these sources, small l, this is small l. So this, if this condition is met, then they are considered to be spatially coherent. So we discussed about the temporal coherence and spatial coherence. Now, this coherence is very important for holography. As we discussed during the introduction, for holography we need interference, and for interference we need coherent beams. And here we discussed about how far incoherence can be tolerated also, right? Like partial coherence we discussed. So these are the characteristics. So if you want a stable interference fringes, so that they are recordable, the maximum path difference between the object wave and the reference wave. Now you correlate it with the two, right? You can see here also, this you can consider S1 as the object wave and S2 as the reference wave. You can consider this eye, my left eye, as the object wave, and the right eye as the reference wave. If you consider this way, then the maximum path difference between these two sources should not exceed the coherence length. It should not be more than the coherence length, or the phase difference between these two sources, from these two sources, should not cross over the coherence time. Further, the spatial coherence is important so that the waves scattered from different regions of the object. Yeah, this is very important. See, your object is not a small object. It's not a point source. So if an object has a length, right? So from different points of the object, there will be more scattering. So all these scattered waves will have a phase difference, and this phase difference over a period of time, over a period of length, should be maintained. And if that is maintained, then interference rings will be formed for different parts of the object, right? And so interference can happen for different parts of the object, so image can be created. So we can see here how temporal coherence is important and how spatial coherence is important. Spatial coherence is important more from the dimensions of the object point of view, because scattering is taking place at different points of the object, and temporal coherence will be important for each point source for distance, coherent length. That means you should obtain interference within that length only. So I hope I have cleared these aspects. So I think we close it, and we will move in the next video to the latter part of the holographic discussions. So thank you very much. Close it now.